Hello everyone. Today we are going to talk about cardiac cycle. In this lecture, in this video we will be discussing the physiology of cardiac muscle, anatomy of the heart. So these are basic knowledge you should have about the heart, physiology of the cardiac muscle, anatomy of the heart, electrical activity of the cardiac muscle, how cardiac electrical activity is demonstrated in an electrocardiogram. So we will be learning sequential pattern of contractions and relaxations in the heart, which results a normal pattern of blood flow within the heart, pressure and volume changes of atria and ventricles, right? So sequential pattern of contractions and relaxations in the heart, which results a normal pattern of blood within the heart, pressure and volume changes of atria and ventricles, pressure and volume relationship of the left ventricle. How to relate the above events to your ECG, jugular venous pressure tracing, ventricular volume curves. How are the heart sounds and murmurs are being produced? So ECG, jugular venous pressure tracing and ventricular volume curves. We will be discussing these events, right? So how are the heart sounds and murmurs are being produced? So the basic anatomy of the heart, as you can see, this is the aorta, this is the superior vena cava, and this is the pulmonary artery. So this is the pulmonary vein over here, and this is the right atrium and the pulmonary valve. This aortic valve, this is the aorta, and this is the left atrium. This is the aortic left ventricle. So between this, you find the mitral valve, right? So this is the right ventricle, and this is the tricuspid valve. So conduction system of the heart. So you can see the electrical system of the heart. So this is the sinoatrial node in the right atrium, and this is the middle internodal tract. This is the anterior internodal tract. This is posterior internodal tract. So this internodal tract means between SA node and the AB node. Then over here you find the right bundle branch. This is the left bundle branch. This is the right bundle branch. This is the left bundle branch of AB node. So these are the conduction pathway, this Purkinje fibers and bundle of his, and this is known as Bushman's bundle. So these Bushman's bundles goes from SA node to the right to the left atrium. So this is his bundle and bundle of his and Purkinje fibers. They go to left and right ventricles. So these are the basic components of an ECG. You can see the PR interval, which resembles the SA node depolarization or SA node firing, and then this P wave, then the PR segment, and then the QRS complex. So the QRS complex stands for ventricular this ventricular depolarization, ventricular firing. PR segment usually indicates a time gap between the time taken for the SA node, the depolarization of the SA node that goes to the AV node, and AV node has to spread them to the ventricular muscle. So that time taken by the AV node is shown here by the PR segment. So you can note that this PR segment, although it is known as PR segment, it does not actually indicate the gap between P and R, but instead it represents P to Q interval, right? So, but it's known as PR segment. Then QRS duration. You can see it resembles ventricular depolarization. And meanwhile the atrial repolarization takes place, but because of this high force that takes place in the ventricular ejection or ventricular depolarization, QRS complex is weak. So that atrial depolarization gets hide away, right? QRS duration, and then ST segment shows the ventricular repolarization. So this is QT interval. Yeah, that is it, right? So cardiac cycle is a sequence of events that occurs and repeats with every heartbeat. The sequence of events that occurs and repeats with every heartbeat from the beginning of one heartbeat to the beginning of the next. It comprises series of contractions in the heart that pressurize different chambers. causing blood to flood in one direction. It has a series of contractions in the heart that pressurize different chambers, causing blood to flood in one direction. How is this cycle initiated? Each cycle is initiated by a spontaneous action potential in the sinoatrial node. Each cycle is initiated by spontaneous action potential in the sinoatrial node. Due to this conduction originating at the sinoatrial node, the atria contract together. Then, after a short pause at the atrioventricular node, the two ventricles contract together. This lag is due to a time gap between the electrical conduction and the actual application of the myocardial force. So as you can see, each cycle is initiated by a spontaneous action potential in the sinoatrial node. During the conduction originating at the sinoatrial node, the atria contract together. Then, after a short pause at the atrioventricular node, the two ventricles contract together. This lag is due to the time gap between the electrical conduction and the actual application of myocardial force. So as you can see, first of all, this SNR, known as a pacemaker, the cycle is initiated by spontaneous action potential, right? So it happens spontaneous. So then this SNR, the atria contract together. So you can see that here from this SA node, there's electrical transmission impulse is transmitted to the left atrium too by the Bushman's valve. So then SA node spontaneously get depolarized, then that is transmitted to Bushman's valve. Then the both left and right atriums, they left and right atria, they contract together, right? Then after a short pause at the atrioventricular node, the two ventricles contract together. This lag is due to a time gap between the electrical conduction and the actual application of the myocardial force. The contraction of the atria, both left and right, physiologically precede that of the ventricles, both right and left. So first of all, in its precedence, what happens first is the contraction of atria. Only after that, contraction of ventricles take place, right? This contraction sequence allows the separation of the right and left heart, at least functionally, as two separate circuits. So this contraction sequence allows the separation of the right and left heart as functionally. Functionally, they can act as right and left heart functionally, right? Yeah. So it's kind of like mixed. I thought it's like this, but it's like this. So this get contracted first, this get contracted first, then this pumps blood, and then this blood pumps. So this delay can help in functionally difference. Like there are two circuits, right? This is for pulmonary circulation, this is for systemic circulation. So these are two circuits. We can act as two circuits with a delay, right? So let's see the events of the cardiac cycle one by one. The cardiac cycle is divided into two main phases: diastole, during which the ventricles are relaxed and are being filled with blood; the systole, during which the ventricles contract and eject the blood into great arteries. Each of these phases are further subdivided into small phases. So there are two main phases in cardiac cycle: diastole and systole. In diastole, ventricles are relaxed and they are being filled with blood. Systole, ventricles contract and eject the blood into arteries. Furthermore, few basic principles we have to know before going into the cardiac cycle is that blood always flows from high pressure to low pressure. Contraction of a cardiac chamber increases the pressure within the chamber. So whenever the chamber is contracted, pressure within the chamber goes high. Valves open or close depending on the pressure gradient across the valve. Cycle starts with the firing of SA node, which leads to atrial depolarization. Shortly after this, atria contracts. So this is known as atrial systole. Contraction increases the pressure inside atria, forcing the blood into the ventricle. So you know that when this contraction of atria happens, is pressure increases. So when pressure of atria increases more than the pressure of this right ventricle, blood from atria goes down into the right ventricle. This is an active process and accounts for 30% of ventricular filling. By the moment atria contracts, AV valves are already opened and 70% of the ventricles are filled with passively flowing blood. So before this atrial contraction takes place, the blood that has been accumulated in the right atrium was filling passively into the right ventricle. 70% is of the blood is filled by this passive flow. Only 30% is filled by this contraction of atria or atrial systole. So you can see that how this when this left ventricle volume goes left ventricle volume goes up, so we can track this, right? So yeah, so you can see that a left ventricle volume is the highest, right? uh, okay, let's go on to the next slide. So you can see here it's been tracked against everything, and now we are going to detect the pressure in each of the parts of the heart during these different phases of cardiac cycle. So you can see first of all in the left atrium, right atrium is where the blood gets filled, right? So so in the atrial contraction, this uh, this is left ventricle, and this is aorta. So in the atria systole, we have the higher blood pressure in atria. In the atria diastole, atrial pressure is low, right? Um, here you can see here in the left atrium the pressure is high, but in the right left ventricle pressure is low in the atrial systole. At that time ventricles are diastole, and when the atrial diastole takes place its blood pressure is low, and then atrial ventricular systole becomes, so it gets into high depolarization, like a huge pressure increases there, a huge contraction occurs with the ventricle, huge pressure increase. So then uh, you know blood is going to be pumped out. So here, when the pressure is increasing at one point, the pressure of the left ventricle exceeds the pressure of the aortic valve. Then, across a pressure gradient, this valve, aortic valve, opens and blood from left ventricle goes into aorta. So then, at the end of the aortic systole, ventricular systole, aortic valve closes as the pressure goes down in the left ventricle than the aorta. Yeah, after pumping blood, aortic valve closes, right? So then again this left ventricular pressure goes down because blood is now pumped out. So at one point, this left ventricular pressure goes down the pressure of left atrium. Then again, blood will come to allow blood flow from a left atrium to left ventricle. This AV valve or the mitral valve opens, right? So that is demonstrated. So the aortic in the aorta, you can see after aortic valve closes, its pressure also has been going down, right? Because blood is going to be filled. So that is it, and this shows the whole thing that within the electrocardiogram also, right? So you can see this is the QRS complex that happens when the ventricles are going to contract. Then here PQRS, so this segment from S T happens when the ventricles pressure keeps when the ejection takes place, right? Then yeah, that's it. So these are the phases of the cardiac cycle. First one is atrial systole begins. So then atrial systole begins. Atrial contraction forces blood into ventricles, right? So this is P valve depolarization. You can see this atrial systole begins. Atrial contraction forces blood into ventricles. So that is the P valve. Then QRX, ventricular systole, that means ventricular contraction. Ventricular contractions pushes the blood out. So that is represented by QRS. Ventricular systole, second phase, semialveolar valves open and blood is ejected. Then next one is ventricular systole, and next one is ventricular diastole. So ventricular diastole is represented by ventricular repolarization. T wave. QRS complex represent ventricular systole, that means ventricular depolarization, right? So it has two phases. First one is ventricular systole, first phase where the ventricular contraction pushes AV blood closed, semialveolar valves open and blood is ejected. That is what is. Then the fifth one, ventricular diastole late. Chambers relatively chambers relax and blood fills into ventricles passively. Chambers relax and blood fills into ventricles passively. So if I may go through this again, you can see first of all what happens is blood keeps getting filled into the ventricles, right? So thereby because of the atrial contraction. So that is represented by P wave. So it's also called as atrial systole, right? So then we have the QRS complex, which shows the ventricle depolarization. That means blood keeps filling into the ventricles. Ventricular contraction pushes AV valves closed. So this ventricles keeps contracting, and then blood is taken into the then when ventricular keeps contraction and AV valves are closed in the first phase. Right? AV valves means atricular ventricular valves are closed in the first phase. Then semialveolar valves open and blood is ejected. So here this ventricular contraction pushes AV valves closed. Then blood keeps open and this semialveolar valves are increased, and then this will eject blood. So that is ejacular phase, ejecting phase, right? Then here these AV valves are closed because when this blood is pumped from atria to ventricles, the valves were closed. So the AV valves are closed in this phase and ventricular contraction keeps happening. At some point when this contraction increases, pressure within the ventricles increases than the pressure of aorta, and then semialveolar valves opens and then blood is ejected, right? Ventricular diastole. So what happens in ventricular diastole is semialveolar valves close and blood flows into atria. So the semialveolar valves are closed and blood flows into atria. So here what happens is that these semialveolar valves get closed, right? So blood flows into the atria. So now this ejection phase is over. Then these semialveolar valves are closed, blood are flowing into the atria, and these ventricles are in the relaxed form. That means a diastole, right? So it is actually shown by T wave, ventricular repolarization. Then the ventricular diastole late one is this AV valves are opened and then blood keeps filling into the chambers, ventricular chambers. Chambers drops and blood fills ventricles into ventricles passively. That is it. So if we move to the next, yeah, this is ventricular diastole. So this is ventricular, yeah. So you can see the places at which other stuff are here. So atrial diastole here, atrial systole also happens here, atrial diastole throughout the rest of the cardiac cycle. Ventricular diastole here, the atrial systole, ventricular diastole, the ventricular systole happens, and then ventricular diastole happens again. So the phases of cardiac cycle, we find four of them. Phase 1, period of filling, diastole. Phase 2, isovolumetric contraction. Phase 3 ventricular ejection. Phase 4 isovolumetric relaxation. Phase 1 filling of the heart or diastole. Both ventricles and atria are relaxed at the beginning. So we have atria and ventricles relaxed at the beginning. Atrioventricular valves remain open. Both aortic and mitral valves are closed. Mitral valves are closed. Right atrium um, Right atrium receives blood from inferior vena cava and superior vena cava. Left atrium receives blood from pulmonary veins. Early ventricular filling 70% is passive. Towards the end of the diastole, atrial systole occurs and pushes the remaining blood inside the atria into ventricles. Atrial systole is an active process and accounts for 30% of ventricular filling. During the atrial systole, venous drainage to atria stops and there can be some regurgitation. So what here means is that we remember the name of the phase is diastole, right? So we are referring to the ventricles here. So the ventricles are at diastole, but at the end of the diastole, we find atrial systole occurring and receive the 30% of blood is pumped active into the ventricles. So during atrial systole, venous drainage to atria stops. So atria means the venous drainage to atria stops and there can be some regurgitation. So it means venous drainage means superior vena cava and inferior vena cava blood is draining into venous blood is draining into atria. That is stopped while this atrial systole takes place and some regurgitation. That means some blood will go back into the either superior vena cava or inferior vena cava during atrial systole. If you remember, this may cause a rise in the pressure in the right, the inferior vena cava, superior vena cava, and then jugular venous pressure goes up, and it is represented by a wave in the jugular venous pressure, right? Phase 2, isovolumetric contraction. Ventricles are filled with maximum amount of blood. So ventricles are filled with maximum amount of blood. So you can see that both AV valves are closed due to high pressure inside the ventricles than in atria. So ventricles are filled with maximum amount of blood. Both AV valves are closed due to high pressure. So in phase 2, isovolumetric contraction, it means that the ventricle volume is equal. It's not thorough changed at all. So no more blood is being filled into the ventricles. So AV valves are closed. So because when the valves are closed between atria and ventricles, no more blood can be pumped into the ventricles, right? So we maintain a constant volume in ventricles, and that is why it's called as phase 2 isovolumetric contraction. So closure of AV valves gives the first heart sound. Semi-ulnar. So why is this AV valves are closed? Is because this high pressure inside the ventricles than in the atria. So ventricles are filled with the maximum amount of blood, that means 120 milliliters is the ideal value of a end diastolic volume, right? So semi-ulnar valves are closed at this moment. Semi-ulnar valves are first closed in this phase 2. Ventricular muscles start to contract without changing the volume of the ventricles but building up pressure inside the ventricles. So we talked that when contraction of the chamber occurs, the pressure inside the chamber goes up. So to build up this pressure, ventricles keep contracting without changing the volume of it. So it is known as isovolumetric contraction. With the pressure building up inside the ventricles, AV valves bulge towards atria, giving up a small pressure rise within the atria. This is represented by the A wave of the JVP tracer. So when the pressure building up inside the left ventricles, AV valves bulges towards the atria, giving a small pressure rise in the atria. This is represented by A wave of the JVP tracing. Okay, I'm really sorry because I mentioned earlier that this A wave is caused by regurgitation from blood from atrium to superior vena cava, but it's not true. Usually JVP tracing indicates the pressure in the atrium. So that was I kind of got confused there. So that is represented by A wave because when A wave when the pressure inside ventricles is high, it's some AV valves. AV valve kind of bulges towards the atria. It doesn't open but bulging towards the atria takes place and giving a small pressure rise in the atria. This is represented by A wave of the JV tracing. Once the pressure inside the ventricles exceed the pressure inside the aorta, when the pressure inside the ventricles exceed the pressure inside the aorta and pulmonary artery, respectively, the semi-alveolar valves open and ventricular ejection begins, right? So in the phase 3, with ventricular ejection, blood is squeezed into the arteries. This pulls down AV valves towards the ventricles, giving a pressure drop inside the atrium. So this is shown by X descent in jugular venous pressure curve, right? Curve, okay? So ventricular pressure rises into a maximum and then gradually falls. So during this ejection phase, so first of all, LV has been increased to 120, right? And the right ventricle, it has been increased to 25. So 120 exceeds 80 and 25 exceeds 10, which are the respective pressures in the aorta and pulmonary artery. So then these semialveolar valves open and ventricular blood ejection occurs in the arteries. When ventricular pressure drops, so after that ventricular pressure keeps dropping, right? Below the pressure inside the great arteries, semialveolar valves close and ventricular systole comes to end. So after the blood pressure has been dropped inside the gray ventricles below arteries, that means ventricles, the semialveolar valves close and the ventricular systole comes to an end. So this pressure has to be definitely below, you can see as here. So this valves close, but it's above now the atrial aortic pressure is above 80, it's not 80 again, okay? So the pressure at which the valves close is not 80, it's above 80. Closure of the semi-ulnar valves give the second heart sound, right? During ventricular ejection, only 70 to 90 milliliter of blood, that means a stroke volume from EDV, is ejected. Around 50 milliliter remains within the ventricles. That is known as end systolic volume. So the volume at the end of the systole. We um, express the amount of in percentage of EDV and it is called ejection fraction. So don't mistake, this is end diastolic volume, right? So the initial amount SV means the that volume that's been pumped out. So SV equal to EDV minus ESV and diastolic volume minus end systolic volume. So it is then multiplied by 100 gives out the percentage that has been pumped out. This can be used as an index of ventricular function. To check whether the ventricles function better, we can use this as an index. Okay. Phase 4, isovolumetric relaxation. After the ventricular systole, the ventricular muscles start to relax. So after the ventricular